Hello, everybody. Mr. Klein here, and today we're going to talk about my buddy Gale, specifically the misadventures of Gale the birthday clown. These are related rates problems, each one of them centering around the hijinks of this goofy, sad clown. And I think if you want to understand the character who we're going to be exploring for the next couple of classes, this sentence says it the best. Two sentences. Gale dreamed of being an actor. He became a birthday clown. All right, so here we go. Let's see what Gale is up to. Little Billy's parents hired Gale the birthday clown to perform at Billy's 5th birthday party. While the children arrive, Gale is blowing up a fun spherical shaped balloon at a constant rate of 100 cubic inches per minute. How fast is the radius growing when the sphere contains 50 cubic inches of birthday cake smelling clown breath? All right, so first thing, most importantly, notice what I did there is I let you know that Gale's been eating the cake. Second thing is it's a really good idea to highlight where the actual question happens. There's a lot of information, and you want to be able to focus your attention on what you are looking for. Usually it comes in the last sentence, and this is no different. It said, how fast is the radius growing? And let's keep in mind that that is not asking us for the radius of the balloon. It's asking us for the rate at which that radius changes. So the thing we're trying to find in this problem is dr dt, the rate of change of the radius over time. All right, now let's go back and let's pick apart the other pieces of information that were given to us in the problem. Right here it says that he is blowing up a fun spherical shaped balloon at a constant rate of 100 cubic inches per minute. And it also tells us that at the instant that we're trying to measure the rate of change of the radius, there are 50 cubic inches of volume in the balloon. So this would be the volume. And this, notice that it's a rate, would be the rate of change of the volume. In general, when you're tackling one of these more complicated related rates problems, this is a really, really intelligent way to start. To highlight the question, identify symbolically what it's looking for, and then label all the other numbers in the problem to see what they are. Okay, so from here, it is time for us to write an equation, kind of like what we were doing last class. And I want to remind you, I've got a balloon here, that as the volume changes, so does the radius. So volume bigger, radius bigger. Volume smaller, radius smaller. And that there must be an equation that relates the size of that radius to that volume. Turns out you studied that equation when you were back in geometry. And that equation goes a little something like this. The volume of a sphere is equal to 4/3 times pi times the radius of the balloon cubed. So once you have identified these things, a good idea is to write an equation that relates them. Last time we had a 3-step process. This was step number 1. Right? Now the next thing that you're going to do is you're going to take the derivative of both sides with respect to time. I didn't write it this way last class, but I'm going to right now. In a sense, what you're doing is taking d dt of both sides of the equation. Okay. So you don't have to write those symbols, but I'm going to right now just to emphasize how we find the rate. On this side, you can see that this is saying the rate of change of the volume with respect to time. On the other side, see how the variable that we're taking the derivative with respect to and the variable that's in the equation, they don't match. And there's a reason they don't match. It's because this radius changes as time goes by. So this is actually a moving quantity. And so you want to keep in mind that this is going to be a chain rule problem where the R is sort of like an inner function. And that will be the case anytime the variable that you're taking the derivative with respect to and the variable in the equation don't match. So over here, chain rule, we're going to get a chain of two derivatives. The outside function is 4/3 pi times something cubed. If you take the derivative of that, you get 4 pi r squared. What's that, Mr. Klein? Isn't that the surface area formula? Well, yes, it is. There's actually a reason that if you take the derivative of the volume of a balloon or any sphere like this, what you're doing is looking at the rate at which it grows. And when it grows, what you add is a little shell around it. And that shell is like a surface area. So that actually kind of makes sense. Now, because of the chain rule, we now have to take the derivative of this inside function. If there's anything that you get out of me doing this problem, make sure that you get this. The derivative of r with respect to time would be dr dt. So this is the proper derivative equation. As a general rule, with all these related rate problems, every time you see a variable, you're going to take a regular derivative and you're going to add a d variable d time to it. That will always work. All right, so now let's plug in the information that we know. I'm going to come back here and note that we're looking for how fast the radius is growing. So what we're looking for is this. Notice I highlighted that in the same color that I highlighted it up here. That's just to kind of keep me organized. And then that means that we need two pieces of information. We need this and we need this. And it just so happens that if you look up at the top of the page, we know this is 100 and this is, oh, crumb bums. We were not given R, were we? What were we given instead of R? Ooh, we were given volume. So this is one of the reasons that today's problems are a little more challenging than what we did last time. Because if you want R, you're going to have to come back to the original equation, which looked like this. And you're going to plug in the volume. And then you're going to solve that equation to figure out what R is. And the way you would solve that is you would multiply by 3/4 and divide by pi. So over here we get 3 times 50 over 4 pi is equal to R cubed. And then we would take the cube root of both sides. So R is going to be equal to the cube root of 3 times 50 would be 150 over 4 pi, which if you chuck that into your calculator, you're going to get a number. I just happen to have that number right here. It is 2.29 inches. So that's what goes here. So let's see. Our final answer, our last step, is to now solve for the thing we're looking for. 100 is equal to 4 pi times 2.29 squared times dr dt. So dr dt is equal to 100 over 4 pi times 2.29 squared. If I may say a word about using the calculator on one of these problems, I would strongly encourage you to hang on to your numbers and don't round them. What I mean by that is at this stage, when we found R, we could do that as math cube root of 150 divided by 4 pi in parentheses. So there's the 2.29, right? When I evaluate at this stage, I'm going to go 100 is divided by parentheses 4 pi times, grab the number from up here. Now I'm not rounding, squared. There's our answer. Now, you obviously are going to have to round your answer here at the end. But if you round early, what happens is it throws this number off by quite a bit. So 1.524, and our units would be radius over time is inches per minute. Let's see what Gale gets up to next. Number 2. Gale popped most of the balloons. Annoyed with their clown, Billy's parents have assigned him the task of filling up the birthday boy's new pool. Can't see how any problems are going to occur there, right? Gale reads on the box that the cylindrical pool has a radius of 5 feet. Gale is pumping at a rate such that the height of the water changes at a constant rate of 0.1 feet per minute. So the water is filling. Water is seeping out of a hole in the bottom of the pool at a rate of 3 cubic feet per minute because Gale accidentally walked over it in his giant clown shoes. At what rate is Gale pumping water into the pool? Some of these problems are going to benefit from you drawing a picture, and this is definitely one of them. So let's look at our pool. Our pool is a big old cylinder. And here is a sad clown who is got some really big shoes. And what is he doing? He is using a hose to put water into the pool. So right here, water is coming in. Let's use the color of water. Okay. And then there's water in the pool. But recall that there's also this hole right here. And so there is water that is leaking out onto the ground. So we've got a rate at which water is coming in, and we've got a rate at which water is coming out. And this is a brand of problem that we're going to continue to visit throughout the year in calculus. The idea that if you want to know the rate of change, in this case, the rate of change of the volume of the pool, it is equal to the rate at which water comes in minus the rate at water comes out. It's the difference of these two rates that gives us our rate of change. So rate in minus rate out. Okay. So with that in mind, let's go back to the question. The question asked, at what rate is Gale pumping water into the pool? So what it's asking us for is R in. And we were given some information. It says that the radius of the pool is 5 feet. It also says here that the height of the water changes at a constant rate of 0.1 feet per minute. So that would mean the rate of change of H for height, is 0.1. Finally, it told us that water is seeping out at a rate of 3 cubic feet per minute. So this right here, I'll write it below because I don't have room, is the rate out, which is equal to 3. So in this problem, we are trying to find the rate in. We are familiar with the rate out. We know that that's 3. So if we want the rate in, what we're going to have to find is this. Picture how if we could plug a number in right here, then we could just add 3 to it, and we would get our answer. So it's important to recognize that the rate of change of V is just a fancy way of saying dV dt. T. And this is what we're going to try to find. All right. Here we go, ladies and gentlemen. Step one. Write an equation that relates the volume of the pool to its radius and its height. Since this is a cylinder, it would look like this. I put the multiplication right there to emphasize to you that we have two separate equations. We have this one and this one. So in step two, when you take the derivative, you're going to be using the product rule. Okay, we did a little bit of this last class. Hey, just for kicks, pause the video and see if you can do this on your own, and then unpause and check your work. Okay. I'll assume you've tried it already. Here's what your derivative should look like. The derivative of pi r squared with respect to time would be 2 pi times the inside function is r. You treat this like an inside function because r is changing in some way with time, multiplied by the rate of change of the radius over time, multiplied by, leave the h alone, plus, leave the pi r squared alone, and then multiply it by the rate of change of h would be dh dt. Okay, so there's our equation. Cool. The thing we're looking for is how the volume is changing, which means that we're going to need this, 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 and this. Now, I know that the rate of change of the height is 0.1, that was given, and I know that the radius is 5. We were not given the height or the rate of change of the radius. However, we know something really important about this, don't we? We know that the pool is filling up this way and that it's not expanding. It's not getting bigger in this direction. That would be kind of weird if it was, right? So the rate of change of the radius is in fact 0, which allows you to cancel this entire portion of the equation. So step 3, the volume of the pool would be equal to just, I'm grabbing this piece over here, pi times 5 squared times 0.1, which if we throw that into the calculator is equal to 7.854 cubic feet per minute. And that means that our answer we're going to get from bringing back this equation from above. The rate of change is equal to the rate in minus 3. So 7.854 is equal to the rate in minus 3. And if we add 3 to both sides, the rate at which Gale is adding water to the pool is equal to 10.854 cubic feet per minute. All right, ladies and gentlemen. Now we're cooking. Let's take a look at one more. Flip the page. Okay. Now, this is the first kind of real problem in the sense that this one's got stakes. The answer matters. Take a sip of coffee here. That is good. Made it in my French press. Gale is tired and a touch lightheaded after blowing up all those balloons and the kiddie pool. He waddles inside and opens up a nice, refreshing can of soda. By the way, don't call it pop. That's annoying. Soda, but accidentally knocks it over on the table where Billy's friends have stacked all the gifts. Okay, you see the conflict developing. The soda spills out at a constant rate of 7 milliliters a second and forms a cylindrical spill. Gale can tell that when the radius of the spill is 5 centimeters and the height is 2 millimeters, the height grows at a rate of zero point 0.1 millimeters per second. Gale is he's a very perceptive clown. If the radius is growing faster than 1 centimeter per second, Gale will not be able to save the gifts. The party will be ruined. Will the presents be ruined? So there's the question. And the way that we answer that is by this. If the radius is growing faster than 1 centimeter per second. So what the problem is asking us to do is to figure out the value of the rate of change of the radius of this spill. Just to kind of drive home what we're doing. Here's the spill from the soda. It's a little cylinder. There's the radius, and it's growing in this direction. Okay. It's also growing in, here's your height. It's also growing in this direction. So the height and the radius are changing this time. So we want to know what this is equal to. And when we're done, we're going to compare it to 1 centimeter per second. All right. So let's label the information that we've got here. It says the soda spills out of the can at a constant rate of 7 milliliters per second. I would like to point out something that you should know from chemistry, which is that a milliliter is equivalent to a cubic centimeter. So this is saying that the rate of change of the volume of the spill is equal to 7 cubic centimeters per second. Gale can tell that when the radius of the spill is 5 centimeters, so R is 5, and the height is 2 millimeters. We have to have the same unit, so I can't plug in a 2 here. I'm going to have to convert this to centimeters, which would make it 0.2 centimeters. And the height grows at a rate of 0.1 millimeters per second, which would be like saying that the rate at which the height changes is move the decimal point over one place, 0.01 centimeters per second. Okay. So there's the numbers we're going to use. Same equation as last problem. Volume is equal to pi times radius squared multiplied by height, which means that this time, when we take the derivative, we're going to get the same thing that we did on the last page. So we got that. And now let's label the pieces. We are looking for this quantity right here. So we need to know this, which was given to us as 7. We need to know the radius, which is 5. And the height, which was 0.2. And the rate of change of the height, which was 0.01. So our last step is going to look like this. 7 is equal to, I'll multiply that together, that would be 2 times pi times 5. That's 10 pi times 0.2 times dr dt, plus, this would be 5 squared is 25, so 25 pi times 0.01. Which means that the rate of change of the radius is equal to, this is just a linear equation with this as your variable. So you're going to subtract this from 7, and then you're going to divide by the coefficient. So your answer will look like 7, take away 25 pi times 0.01, all divided by 10 pi times 0.2. Which is equal to, here's our moment of truth. Boom, 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 boom. Will the presents be saved? Take that, divide it by the quantity 10 pi times 0.2. I got 0.2 9, 9, which is less than 1. So, oh, happy day, ladies and gentlemen. The presents are saved. Which means the party can continue. And we'll find out what Gale is up to next time.